Huffman coding is an efficient algorithm for lossless data compression. Developed by David A. Huffman in 1952 at MIT, it's a cornerstone in information theory and digital communication. It forms the basis for modern compression formats like zip, JPEG, and MP3. Huffman coding assigns shorter binary codes to frequent symbols and longer codes to less frequent ones, reducing total bits. Every digital file is made of symbols. Traditional fixed-length encoding uses the same number of bits for each symbol. For example, ASCII uses 8 bits per character, regardless of frequency. This is inefficient because common characters appear much more frequently. Huffman coding eliminates this inefficiency through variable length encoding. It uses shorter bit sequences for common symbols and longer ones for rare symbols. The codes are designed so no code is a prefix of another, ensuring unique decoding. Huffman's algorithm provides a systematic way to achieve this optimal prefix-free encoding. Huffman coding involves 2 steps: building the Huffman tree and generating code words. First, the frequency of each symbol in the data is computed. For beekeeper, frequencies are E, 5, K, 1, P, 1, B, 1, R1. Since E is most common, it will have the shortest binary code. Next, the algorithm constructs a binary tree, the Huffman tree. It creates a leaf node for each symbol with its frequency, then places all nodes into a priority queue. The 2 lowest frequency nodes are merged into a new node, summing their frequencies. This new node is reinserted, repeating until one root node remains, forming the Huffman tree. Left edges are assigned 0, right edges 1. A symbol's binary code is found by traversing from the root to its leaf. Once the tree is built, we can read the Huffman codes. For beekeeper, codes are E, 0K, 110, P, 111, B, 100, R, 101. Thus, beekeeper becomes BEEKEEPER. The encoded bit string is 10000111000111001. Originally, with 8-bit ASCII, Beekeeper required 72 bits. Huffman encoding reduces it to just 18 bits, a significant compression. Huffman coding is prefix-free, meaning no code is a prefix of another. This ensures unambiguous decoding. A matched code translates immediately. It also guarantees optimality among prefix-free codes when symbol probabilities are known. Mathematically, Huffman coding minimizes the expected code word length, L equals sigma. This method ensures the average code length is as close as possible to Shannon's entropy limit. Huffman coding offers several key advantages. First, its efficiency achieves near optimal compression for given symbol frequencies. Second, its simplicity makes it easy to implement using basic data structures like heaps and binary trees. Third, it provides lossless compression, perfectly reconstructing the original message. Fourth, its versatility allows it to work with any data type: text, image pixels, or sound samples. Finally, it's a foundation for other codecs, with many formats using Huffman coding as a final step. Despite its strengths, Huffman coding has limitations. Its efficiency depends on knowing symbol frequencies beforehand. If frequencies change dynamically, adaptive Huffman coding or arithmetic coding are needed. There's overhead for small files, as the Huffman tree must be stored or transmitted. It's not optimal for correlated data, as it assumes symbol independence. Its limited flexibility means the Huffman tree cannot easily adapt to changing probabilities in streaming data. Several variations improve upon the basic Huffman method. Adaptive Huffman coding updates the tree dynamically, useful for real-time compression. Canonical Huffman coding rearranges code words lexicographically for compact codebook representation. Length-limited Huffman coding restricts code word length, useful in hardware implementations. Each variant balances trade-offs between compression efficiency, speed, and complexity. Huffman coding's simplicity and efficiency make it a backbone of many compression algorithms. It's used in text compression formats like zip, gzip, and TER. In JPEG, Huffman coding compresses DCT coefficients after quantization and run length encoding. In MP3 and AAC, it efficiently encodes quantized frequency coefficients. It's also used in telecommunications to minimize bandwidth while maintaining signal integrity. Furthermore, it's employed in modems, network routers, and file storage systems to reduce redundancy. Compared to fixed-length encoding, Huffman coding dramatically reduces average bit length. Against other variable-length schemes, Huffman coding is simpler and faster, but slightly less efficient than arithmetic coding. Arithmetic coding can reach compression closer to the entropy limit. Nonetheless, Huffman's deterministic nature, low computational cost, and ease of decoding make it practical for many systems. Consider compressing English text. Space, E, and T are frequent, while Q and Z are rare. Huffman coding assigns short codes to common letters, leading to a 40 to 60% file size reduction compared to SCI. This principle underlies many text compression utilities, from Huffman Zip to modern web browser encoders. Huffman coding represents a brilliant intersection of mathematics and engineering. By assigning variable-length binary codes based on frequency, it efficiently reduces redundancy and ensures perfect data recovery. Decades after its invention, it remains the standard benchmark for lossless compression. Whether compressing a web page, an image, or a song, Huffman coding continues to drive digital communication.